In this video, we are going to look a little bit more closely at what probability means in the many worlds interpretation of quantum mechanics. So the Born rule, which says that the probability of some event I is just equal to the square of the probability amplitude of that outcome. This is one of the most important postulates of quantum mechanics, since it's what tells us what we can predict to observe as the outcomes of experiments. In other words, it's fundamental for any observation predicted by the theory. But remember that Everett wanted to do away with any sorts of measurement postulates, which is what the Born rule is, and keep only what the theory tells us. As such, he must be able to derive the Born rule using only the theory. And so Everett, in his 1957 thesis, says, "The new theory is not based on any radical departure from the conventional one. The special postulates in the old theory, which deal with observation, are omitted in the new theory. The altered theory thereby acquires a new character. It is to be analyzed in and for itself before any identification becomes possible between the quantities of the theory and the properties of the world of experience." So what he means here by the quantities of the theory would be something like the wave function, and then the properties of the world of experience would be the outcomes of experiments. So for instance, we can't just postulate that the wave function, when it's squared, becomes the probability. This has to be something that comes from examining the theory, not something that's just postulated about the theory. He goes on to say the identification, when made, leads back to the omitted postulates. So again, he's saying that we can derive these omitted postulates of the conventional theory that deal with observation, but in a manner that clarifies their role and logical position. He means within the theory. And so again, he's trying to avoid just putting down postulates and trying to actually derive them from the theory of quantum mechanics. But if the theory says that every outcome that can possibly occur does actually occur, then in what sense can the theory account for the probabilistic nature of our observations? To understand this, let us think of a spin-half particle in the spin up along the plus x direction, and we are looking at this in the z basis. We can think of this like a sort of quantum coin where this plus z, so up in the z direction, is equal to heads, and down in the z direction is equal to tails. If we flip the coin once, we expect a 50-50 chance for heads and for tails. But according to the many worlds interpretation, both outcomes actually occur. So remember in the previous video we talked about how it splits the world into two different worlds, and there will be one where the person saw it spin up and the other one who saw it spin down. And both people are real in the literal sense of the word. And so both outcomes did actually occur. And so by measuring in the z direction, we trigger a branching into the two states of heads and observer saw heads, and tail and observer saw tails worlds. These two observers are often called descendants. So they would be the descendants of the person before the experiment was run. But now say that the observer does this n times with n different particles in the plus x direction. For instance, say that the observer does this for n equals 4 times, we would end up with 16 different branches. It would look like this. So down here, the person flips the coin. They could either get heads or tails. Then they could flip it again. In each of those, they could get heads or tails, and so on and so forth. So we see that these are the numbers of each possible combination. We saw that there's only one branch in which we get 4 heads and one branch in which we get 4 tails. But then there are 4 branches where we get 3 heads, 1 tail, 4 we get 1 head, 3 tails, and 6 where we get 2 heads and 2 tails. And so we see the pattern that most worlds will exhibit these statistics predicted by the Born rule. So in this case, most branches, that's 6 out of 16, observe the 50-50 split right here. And so what it's saying is that in 6 out of these 16 worlds that are created from this experiment, 6 of them have a version of you where you got 2 heads and 2 tails. Only 1 out of 16 has 4 heads, and 1 out of 16 has 4 tails. In general, the number of worlds with n heads observed is given by this, which is just the binomial coefficient right here. And this means that the fraction here, so this f subcapital N of lowercase n of worlds in which n heads are observed, would be given by this. So we're just taking our binomial coefficient and multiplying it by this 1/2 to the n, which is just the chance of getting any single one of the branches. So for very large large n, this becomes a well approximated by a normalized Gaussian with a center point of big N over 2 with a half width of the square root of big N over 2. So that would look something like this, where we have this Gaussian right over big N over 2. That should make sense for the coin flips. We would expect to see that if we flip the coin, say, 1,000,000 times, that 500,000 heads would be what we would expect to see. We see again in the vast majority of branches, the observer will observe the 50-50 split, with many fewer observing the highly unlikely all heads or all tails as the number n here increases. So if we did this with, say, big N equals 1,000,000, then at least one universe will observe 1,000,000 heads in a row. An observer is just exceedingly unlikely to find themselves in such a universe. In fact, they will have, according to this, if we just do this calculation right here, about a 0% chance. But if we want to look at this a little bit more precisely, what we find is that we would have 10 to the negative 301,000. And so that's about a 10 to the negative 301,000% chance of ending up in the world that got just heads. To put that in perspective, you have about a 1 in 3 million chance of winning the lottery, which is about a 3 times 10 to the negative 7%. So you have about the same chance of winning the lottery 33,444 times as you do of ending up in one of those all heads worlds. Even with just n equals 100, and that's because most computers can't do it with n equals 1,000,000, we get that in all heads would be about a 7.9 times 10 to the negative 27% chance, whereas getting anywhere between 45 heads, 55 tails, or 55 heads, 45 tails is about 73%, and anything between a 40-60 or 60-40 split is about 96% chance. So we have a 96% chance of, say, getting 60 heads and 40 tails, all the way to 40 heads and 60 tails. And you can see my calculations for this right here. So we get the about 73% for this one between the 0.45 and 0.55, and the 96% here for between the 0.4 and 0.6. So most things are going to end up in that small range. Anything outside of this small range becomes just exceedingly rare until you get to that point where it's either all heads or all tails, where we have just this extremely small percent chance. And again, that's just with the n equals 100. If we were doing this, say, for the n equals 1,000,000, it's an even smaller percent chance for that. But then we have to ask ourselves, what happens if we do not have a 50-50 chance for the two outcomes? In other words, what if we have something like this, where we have this p and this q here, which are the percent chances, and they are not equal to 50%. In Everettian terms, the p and q here are called the branch weights for spin up along z and spin down along z, respectively. So those are just the probability amplitudes, but now we're saying that they are not equal to each other. For n equals 4, we would now have the branch weights given by this. So for the 4 heads, it would be the p to the 4th power. For 4 tails, q to the 4th power. The 2 heads, 2 tails would be p squared times q squared. In general, this will end up being something like this. The Born rule tells us that for n flips, the probability of H is n times p, where if p is, say, 0.90 and we perform 100 flips, we expect to get 90 heads. So we would have an unfair coin in this case. We therefore need to weight the worlds, so we have to multiply by a weighting factor like this. So what we have is this one in gray right here in the middle. This would be if it's 50-50, but if we multiply it by this weighting factor, which is shown up in this dashed line here, it moves it over to this point right here, where it's n times p. So if p was greater than 0.5, for instance, it would shift you over towards getting all of the same thing for each n on there. So what we see is that the peak is then around the n times p, where if we have p equals 0.5, that's just a special case of this. But just what are these branch weights? Well, these are the squares of the amplitudes of the different branches, such that if we have this for our wave function right here, then the branch weights are just the c sub I squared. But this is just the Born rule. So one way of thinking about the probability in the many worlds theory is in one of these sleeping pill sort of thought experiments. So let's say that a doctor tells me that upon waking up after surgery, there is a 30% chance I'll be put in room A, and a 70% chance I'll be put in room B, both of which appear identical from inside. After surgery, I wake and the doctor asks me which room I'm in. Not able to determine which room it is based on its appearance, the best I can do is say that there is a 30% chance I'm in room A and a 70% chance I'm in room B. Similarly, upon performing in a quantum experiment, which has, say, the following state prior to a measurement, before checking the results, the best I can do is say that I have a 1/3 probability of being in a world where we get definite state A and a 2/3 probability of being in a world where I get definite state B right here. But Norson says that this is all circular. So he says that that is the formula for the branch weights. The equation telling us how much to care about each individual branch in the tree is really just the Born rule. So the overall argument has a strong air of circularity to it. If you weight the branches using the Born rule, then the Born rule weighted sense of most of the branches will display Born rule statistics. It seems that we get the Born rule out as a description of the statistics that will be observed in typical branches only because we put the Born rule in as a measure of how much each branch should count in our assessment of what is typical. And so he's saying here that we've not derived the Born rule, we just assumed it, and then what do you know, it looks like the theory works out with the Born rule. But again, we're just postulating the Born rule, we're not actually deriving it. And so there's an air of circularity here. But he continues, there are some deeper concerns as well. For example, the very idea that we should use this unequal weighting seems somewhat in conflict with Everett's overall idea. Recall, for example, Everett's statement that none of the branches is any more real than the rest. But what is the non-trivial weighting function other than some kind of measure of how real exactly each supposedly equally real branch is? Suppose there are just two branches, one, say, in which a red light flashes, with a branch weight of 1/100, and the other in which, say, a blue light flashes instead, with a branch weight of 99/100. Everett would have us say that the vast majority of worlds, namely 99% of them, include a flashing blue light. This may make some kind of sense from the point of view of an external godlike observer who can somehow see that the blue light world is brighter, more intense, heavier, more real. He's saying here that there isn't really any way of talking about what it means for one of them to be more real or weighted higher than the red light world. But in some sense, Everett's whole program is to abandon, as non-existent and meaningless, the idea of such external godlike observers, and instead to exclusively consider what the world is like from the inside, i.e. according to the observers who are part of the world and governed by its fundamental laws. In other words, what do we actually mean when we say the world is 99% and the other world is 1%? Is this just simply counting worlds that have a given outcome to an experiment and dividing by the number of all worlds that branch due to the experiment? If so, how many new worlds are made at each branching event? Presumably there would be enough to give us proper proportions, but why should that be the case? For instance, why should it be the case that if the outcome of some experiment has, say, a 1/3 chance of happening, that at least 3, or some multiple thereof, worlds must branch apart just to ensure that there can be only 1 out of the 3 with the outcome predicted to be 1/3 chance? So essentially what I'm saying here is if we're giving these proportions to different possible outcomes of an experiment, then are enough worlds actually branching out for us to be able to say, well, this is the percent chance that you would find yourself in one of the worlds that had this outcome to the experiment. But in that case, the experiment would have to actually make enough worlds in order for that percentage to be meaningful. Because if we're, say, doing something that has 2 possible outcomes, but one of them has a higher chance, then there really isn't any meaning to saying that one of them is a higher percent chance world. So if a branching event between 2 possible outcomes, one of which is 99% chance of happening, the other just 1% chance of happening, each of these 2 worlds has a version of you who is, according to the theory, just as real as the other. And so in reality, there would only be a 50-50 chance of you finding yourself in one of those worlds. You're either in world A or you're in world B, meaning that if the world branches into one of 2 outcomes, what does it even mean for one of the worlds to be more likely than the other? And so Norson continues here, there has indeed been a trend in the recent literature on this issue away from treating the branch weights as somehow objective facts that we, the theorists analyzing the merits of Everett's theory, must acknowledge, and toward treating them instead as measures of how individual observers within an Everettian world should care about their various descendants. As Simon Saunders has summarized this point, so now he's quoting this other scientist here, in recent years with the development of decision theory methods for quantifying subjective probability in quantum mechanics, the link between probability in the subjective sense and in the objective counterpart has been greatly clarified. Specifically, it can be shown that agents who are rational in order to achieve their ends have no option but to use the modulus squared. So that's that C sub I squared that we were talking about before. So the modulus squared branch amplitudes in weighting their utilities. In this sense, the Born rule has been derived. Then Norson continues, this claim, though, remains controversial, with questions proliferating about the necessity of defining, or indeed expecting, the quote-unquote rationality of agents in the way required by the derivation, the appropriateness and relevance of focusing on how agents who believe in Everett's theory should behave as opposed to explaining why we should interpret our empirical observations in Everettian terms, and even whether the concept of probability can possibly mean anything in a picture where, with certainty, everything that can happen will happen. And there's another question that I've always kind of had about this, but which Norson doesn't really cover here. So when I run an experiment and end up causing a branching event, how is it that I, the me who is conscious of just one of the particular outcomes of the experiment, ended up in the world that I did in fact end up in? Even if we can account for the probabilities of outcomes in this Everettian sense, when I make a measurement, I would still have just one experience of just one single outcome. This means that there are multiple versions of me who also have definite single outcomes, all of whom have the same legitimacy to the claim of being the same me I was prior to the experiment. So prior to the branching event. Yet each version of me is still just one version of myself. I don't experience the smeared out nature of the quantum wave function, and so why is it that I become singly conscious of the single world that I do? So what I'm saying is that right here before the experiment, there is me, I'm the observer, there's just one consciousness. After the experiment, the world splits into two, there are now two consciousnesses, but I will end up in only one of these. So the Everettian theory says that I end up in both of them, but there is a version of me who only, say, would have the spin up in this case, then a completely different version of me who is also conscious of what happened before the experiment, who would say that it is definitely spin down. But I don't experience both of those things, so at some point, the me who is here right now, so the me, say, who is in the blue version right here, had to have gone into the blue version here. But what actually caused them to end up in the blue version there? So this can make sense for what's called quantum immortality, since we know that we will only ever be in a world in which we exist. But if the version of me is alive in both, why do I find myself conscious of one and not the other? So what I mean by the quantum immortality is something like this. So there is a splitting event, a branching event right here, where in one branch I end up dead and the other one alive. And we want to know which one will I find myself in? Well, it'll definitely be the one where I'm alive because I no longer exist in the one where I'm dead. But then, say, a second later or a partial second later, it could be whatever amount of time you want between these. There is another branching event, one where a world is made where I die, another one where I continue to live. Then this happens over and over and over and over again, and what quantum immortality says is essentially that I will always find myself in the universe where I exist, because I can never find myself in a universe where I don't exist. And every time where multiple things can happen, every time where there can be more than one outcome, both of those things or all of those things do end up happening. And so there is always a world where if it splits, there's a version of me that lives, and I will always find myself in that version of the world. So even though it's an extremely unlikely world for somebody to be in, where they live, say, 200 years or 500 years or 1,000 years or whatever, we can always be assured that we will be in the one where we are still alive. And so to you, even though you're in one of the extremely rare worlds, if you were living to, say, 1,000 years old, you will always find yourself in that world. And so that makes sense from the point of view of the many worlds interpretation. It would make sense why I would find myself in the alive world, but not in the me being dead world. So how does this work, though, when both worlds are me being alive? Why would I find myself in the spin up world rather than in the spin down world? There is a version of me that is asking the same question about why they're in the spin down world, but me right now, I'm in the spin up world. So how is it that I ended up in the spin up world? The likely explanation would be that the version of me in the other worlds, like I said, would be wondering the same thing, but each version of me must end up in one of the worlds. But this only answers the question of why I must end up in one of the worlds, but it doesn't say why I must end up in one particular world and not another. And so the question is getting at, what is the mechanism of consciousness splitting? Or is only one of me conscious, and all the other worlds that are made at these branching events are versions of me who are philosophical zombies? So a philosophical zombie is essentially a version of me that's exactly the way I am now. They have said everything and done everything that I've ever said and done, and they will continue to say and attest to things that I will in the future, yet they are not conscious. So that's kind of a deep rabbit hole that you can go down, but what I'm saying here is maybe to answer this question of mine, there is a version of me that is conscious, and all of the other ones are just philosophical zombies. So we could even work out that perhaps then the branch weight is simply just the probability of one of the worlds not ending up as a philosophical zombie. So it's essentially the percent chance of my consciousness actually going into one of the possible worlds. But then the question is, why should this be the case? What, again, is actually causing my consciousness to go into one of the worlds and not the other one? So this doesn't really answer the question. And so this actually reminds me of the teleporter thought experiment by Derek Parfit. And so the question that comes up there is, which of the two people on either side of the teleporter is me? And so this thought experiment goes something like this. So in the top two squares here, we have me, I'm going to teleporter A. In this other world, we have me going to teleporter A. And the teleporter B here in both is millions of kilometers away from teleporter A. I think Derek Parfit put the other teleporter on, say, Mars or something. So then the next step is I actually teleport, so using all the quantum information about every particle in my body, it actually recreates me over on the other teleporter right here. And so again, this happens in both of these possible worlds here. But now we do something a little bit different. In one of them, as is supposed to be the case, the version of me at teleporter A dies, or I believe in Derek Parfit's it said that they were sort of utterly annihilated, all of their particles sort of disintegrated through this teleportation process. So in this one, I end up in teleporter B. This is a version of me that would have all of these same memories as the version of me walking up to teleporter A. But then in this other world, the person in teleporter A, the version of me in teleporter A, does not disintegrate or die or whatever, and so now there are two versions of me. Which one am I conscious of? Both of them would claim that they're the conscious continuation of myself prior to entering teleporter A, but they both would not be the same person. They would not be sharing a consciousness or anything. So the question is, which one is me? And that's kind of the same problem that we're running into with the many worlds interpretation. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.